Okay, I'm very happy to introduce the next speaker, Aida Abiad. This morning, Aida was in Amsterdam, but she made it on time for the talk. We're very happy about that. She's an associate professor at the Technical University of Eindhoven, and she's also affiliated with the University of Ghent. Vrij University of Brussels. Ah, okay. Ghent, now only 0%. Okay. Now only Vrije Universiteit Brussels. And she's going to talk about constructing cospectral hypergraphs.
Thank you, Rafaela, for the introduction. And also thanks to the other organizers for giving me the chance to give this talk here today. It feels a bit weird to talk with a mic, but I've been a bit sick, so I think it's better like this, actually, to use it. So indeed, I'm going to talk about joint work with one of my PhD students, Antonina Kramova. And this is my second paper on hypergraph spectral theory. The first one was with Rafaela and Zhang, that both have been mentioned in Jürgen's talk, actually. So let's go. And I also should say, normally I don't like to use logos for conferences, like for propaganda, but this one I found very cute, so I went for it. So thanks for to the one elaborating it. This is the plan for today. We're going to start with a brief introduction to hypergraph spectral theory. First with a bit of spectral graph theory, which is the background. And then we are going to see two different methods to construct hypergraphs with respect to different representations. I will give you all the background you need. And we will finish with some overview and future research. I should also say before I start that I should thank my student for all the beautiful pictures that appear here. Credits go to her, to Antonina. So as Jürgen already mentioned, like a hypergraph is a generalization of a graph, and then what can happen in a hypergraph is that every edge could have a certain number of nodes. In this talk, I'm going to be concerned about uniform hypergraphs, meaning that every hyperedge has exactly k vertices. Okay. As an example, here I draw one 3-uniform hypergraph on 5 vertices, where the edge set there is 2 hyperedges, as you can see, V1, V2, V3, V3, V4, V5. And also in particular, 2 uniform hypergraphs are just graphs, okay? Yeah, these are the 2 edges that we already mentioned. We also need to define the neighborhood of a set of vertices because we are going to need it in the method that I'm going to introduce to you. Okay, so the neighborhood of a set that we denote as this gamma u is the set of all vertices x such that the union of x plus the set gives you an edge, is part of an edge. So for example, the neighborhood of B3 here is just B1, B2, B4, B5, obviously, right? The neighborhood of B2, B3, which is a set in this case, is only B1, okay? So keep this definition in mind. So let's go back to the basics, spectral graph theory. This is actually my main area of research. I'm not an expert in hypergraph spectral theory, but I'm interested to investigate a bit more on this direction. But going back to the basics, spectral graph theory was born around the 50s, maybe even earlier, I'm not really sure. But what does it do as a field? We want to understand which graph properties follow from the spectra of any associated metrics to a graph. Pick your favorite metrics. Before was a Laplacian metrics. In this talk, I'm gonna mostly be talking about adjacency metrics. Given the eigenvalues of those matrices associated to a graph, what can we say about the graph? Can we actually reconstruct the graph? That's the main question in spectral graph theory. There are many, many known results. This is an old field for graphs, actually. If you want a good, nice overview, this is a survey paper by my 2 supervisors, Van Dam and Hammers, where they give you a short and nice introduction to the field. Some properties that follow from the spectra of metrics associated to a graph are regularity, bipartiteness. As Joost already mentioned, the eigenvalues can be computed in polynomial time, while they can also be used to bound many NP-hard parameters, for example, independence number, chromatic number. Pick your favorite NP-hard parameter of a graph. Many times we can derive eigenvalue bounds, so they are very powerful. And maybe the main open question in this field is by Hammers in 2000. He conjectured that almost all graphs are determined by its spectrum. Here he meant a spectrum of adjacency metrics, and by almost meaning the fraction between graphs which are determined by the spectrum divided by the total amount of non-isomorphic graphs of a fixed order. Okay? This conjecture is still wide open for your information. So this is a very hard problem. There has been progress, partial progress, but not conclusive answers. Okay? So you can imagine for graphs, a big question is still open or conjecture. For hypergraphs, spectrally speaking, is even worse. There is no much known. Okay? So now going to spectral hypergraph theory, the field is a bit newer, as has already been mentioned, from the 90s. And similarly, we aim to obtain information about the hypergraph structure looking at the hypergraph spectrum. Some results have appeared in the literature for spectral hypergraph theory by Cooper and the student of him, Duttel. For example, they prove that regularity and bipartiteness, similarly as for graphs, can also be derived from the hypergraph spectrum. There has been bounds on several NP-hard hypergraph parameters, and in particular with Rafaela and Zhang, we focus on deriving bounds for oriented hypergraphs. They have already been introduced before, so using Laplacian metrics. Okay? There are some other results out there, but not many actually. And in particular, if you focus on spectral hypergraph theory, so the analogy of a spectral graph theory, almost nothing is known, which is very surprising. It's a hard topic for graphs, so I guess for hypergraphs gets even harder. There is a paper by Bu, Zhou, and Wei in 2014, where they show that some trivial graph classes follow from the hypergraph spectra, but that's about all. We could not find any other nice result where you get the spectrum of a hypergraph and you can reconstruct the hypergraph class. So that's actually a bit disappointing. So our wish in this project was to try to fill a little bit this literature gap. How are we going to do it? So in order to understand a spectral hypergraph characterization, so when can you say something about the hypergraph given its a spectrum? It's interesting, you can also look at the converse. When cannot, or which hypergraph property does not follow from the spectrum? And that's what we focus on this talk. We are going to study cospectral graphs and also cospectral hypergraphs and methods to construct them. Cospectral means two non-isomorphic graphs or two non-isomorphic hypergraphs which have the same spectrum. Because by constructing such objects, sometimes they're also called isospectral graphs, we can understand which properties of the object we cannot derive using the spectrum. Okay? For graphs, there are well-known methods to construct cospectral graphs. For example, the most famous one is by Gotzel and McKay on the 80s, but there is also newer ones, quite recent, by Wang and collaborators. And there are some extensions of GM that I did with my supervisor during the PhD. So the goal for this talk is to obtain new methods to construct cospectral hypergraphs. I still didn't define what the spectrum of a hypergraph is, but just that you get an idea what are we going to be doing. Okay. And the spectrum of a hypergraph, of course, it depends on the representation. So there is no consensus in the literature of what is the right way to represent a hypergraph, which is actually very annoying for newcomers like me or maybe others here. So we found in the literature, especially as a reference, we use this paper a lot, that mostly people have looked at adjacency tensors as a generalization of adjacency metrics, if you wish, sometimes called hypermetrics. But there are also some other representations proposed by Feng Li and other authors, where integer matrices that count number of common edges are also used. Okay, we are going to see both, and we are going to see the drawbacks and the benefits of each approach for spectral hypergraph characterizations. So we are mostly focusing on these two. And I didn't mention it, but of course I'm not having oriented hypergraphs here. I'm just having like the simplest definition of a hypergraph. Okay. So this Gotzel-McKay procedure, which I'm going to be called GM switching for in short, it has been extended to hypergraphs, which is actually nice. It's quite a nice finding that we saw in the literature. It has been extended both for adjacency tensors and matrix representations by different sets of authors. As you see, the papers are quite new. But this more recent switching, which is not, is different, it produces different cospectral graphs than Gottsema-K, it was totally open. So for our surprise, and good for us, I guess, we could actually work on these question marks in this project. So let's start with the construction of hypergraphs with respect to the tensor, the adjacency tensors. So first of all, I need to define what the adjacency tensor is. So we say that a K-uniform hypergraph on n vertices has adjacent tensor A of order K and dimension n, where K is the length string of vertices and the dimension is just the number of vertices you have in total. And you define it as this. Okay, so we will see an example in a second that might be more illustrative than the definition. Important to realize, like, this definition is only valid for uniform hypergraphs. So we are going to be focusing on them also because the switching methods we request uniformity, otherwise they don't really work, the extensions. And the drawback of this adjacency tensor is that it's NP hard to compute actually the eigenvalues of such a thing. So that sucks because for graphs was polynomial, for tensors it's NP hard. You can find the reduction in this paper. Yeah, that's a good question. And we have been trying to implement ourselves the existing methods. You need to calculate the resultant of a system of equations, but it's a nightmare. So indeed, application-wise, this might not be the right approach to look at. I totally agree. For that, we also look at the matrix representation. Yeah, I don't know who defined it first, but that's what we follow because we saw it was like the most popular. Yeah. I guess it also represents, yeah, maybe someone knows more about this.
Years ago, so I don't remember exactly, but I do remember that in the end, when you take the sum, I think when you define the spectrum and you need to take like sums of entries, then you do need the normalization. So it's
technical reason,
but it's actually useful when you look at the spectrum. Yeah.
It should be, I guess, like, yeah. We didn't really, for us, it didn't really help, but yeah, we use it because it was like the most common definition we found. But if we want to look at an example of the previous hypergraph, the simple hypergraph that we had, like we can see like this adjacency tensor of order 3, dimension 5 has, well, you see like the blue edge, you have it represented into these 3 vertices, is contained in 2B1, B2, B3, and then also the red hyper edge, it's in B3 before B5. So you get quickly like a large data set thingy there. You see like it blows up compared with the graph representations. That's not so desirable. Okay, and now the definition of eigenvalues. Again, there is no consensus of what is the eigenvalue of a tensor. Again, another drawback of this approach. Makes life hard, but there has been different set of co-authors, Key and Lim, introducing 2 different, actually, definitions. For graphs, they would be equivalent, but for hypergraphs, they give you different things. So the first one uses the determinant, which indeed comes out to solve a system of the resultant of a system of equations, so it's quite nasty. And the second one, which people call it in the literature E eigenvalue, comes from the usual equation that an eigenvalue has to satisfy, but A is now a tensor. Okay. Again, I'm not giving many details here. It gets quite technical. Even the product of a tensor time a vector, that has had to be defined. So this appears in one of these papers. I don't know if I cite it. I think it's one is Key. No, sorry, it's in Xiao's paper if you want more details. But all these operations, someone has had to introduce them, and then we're just following them. Yeah?
Regarding the second definition, if I use a distinction between covariant and contravariant, how does it work?
What do you mean by covariant and contravariant?
Okay, never mind.
Maybe we should discuss later. Yeah, I'm not sure what you exactly mean. But this is the definition we are going to be focusing, because in order for having this is a stronger, it requires a stronger conditions that I'm not putting here. But you need the existence of an orthogonal matrix that commutes with identity matrix and gives you the... So this one has a stronger condition, so we're going to focus on this one for this talk, okay? But you can relate one to the other one. That has also been studied in the literature. Okay, and now if we go back to the origins, to graphs, I already mentioned to you that there exist two main methods. One is GM switching and the other one is WKH. Let's start with GM switching because it's the easiest to explain. So GM switching is a method that guarantees that if you apply it in a graph, you obtain something with the same spectrum. It doesn't guarantee the obtained graph is non-isomorphic, but many times it is in practice, okay? For such a method to work, you need some conditions on your graph. You need that your graph needs to have a vertex partition into a set of vertices which form what we call an equitable partition. I will mention in a second what this could be. And then some condition on the vertices outside the equitable partition. So if I split my vertex set into these n+1 sets, these denote what we call switching sets, okay? And such switching sets need to induce something regular. For example, they could be co-cliques, they could be a regular subgraph, they can be cliques, they can be structures like this. So in my example with only one C1 and D, the C1 is like everything except the middle vertex, okay? So it's a regular graph, it induces a regular subgraph. And everything outside the switching set, so everything outside C1, which is only this central vertex, we put it in D. It needs to have exactly half possible adjacencies towards the switching set, towards C1. It could also have 0 or all adjacencies, but then switching does not do anything. So you would obtain something which is the same, which is isomorphic. So we always want to have this condition to have half edges towards the switching set in order to something interesting to happen. And how switching works, I'm gonna be denoting switching in red. It switches edges by non-edges. So when you had the edges, now you go to the complement to the remaining vertices that were not adjacent towards the switching set, okay? So you see, this is kind of a cute method because it's easy to explain. It's not difficult to find in practice also. And it has been used a lot. I'm not mentioning here papers, but people have been very busy trying to extend, trying to apply. Yeah, well, it has been used in many contexts for different reasons in spectral graph theory. More recently, there was another switching method proposed by Wang and collaborators. And I'm not explaining the proofs of these methods, but the difference comes from the type of orthogonal metrics that you have in the background acting, okay? So now the conditions, I'm gonna focus on the simplest case, which is 2 switching sets. You need an even number of switching sets for this method to work. I'm doing the simplest case of 2 only, and the vertices outside the switching set. For this method to work, you need the switching sets to have equal size, okay? And you also need that this condition is satisfied. I drew it because it's maybe a bit easier to see. So if you look at the neighborhood of a vertex intersecting with the vertices in the switching sets, that difference needs to be constant. It can be a different constant every time, but 2 by 2 needs to be constant, okay? And then for any vertex outside the switching sets, in this case C1, C2, we need to have these conditions. You see, they're a bit more elaborate than before. Now you need that the neighborhood of the vertex V, which is outside the switching sets, intersection, the union of the switching sets is exactly one or exactly the other switching set. Okay, so this is a strong condition. Or you could also have this green condition. However, again, in order to have something non-isomorphic, in order to have a real switching, the red condition should happen. Because whenever you have this red condition, you switch, if you had, say, C1, you switch to C2 or vice versa, okay? So the switching comes always from the red conditions in my talk. Okay. So I hope this was clear because this is the one we're gonna be extending. For graph theory, it gets, I mean, the proof is not extremely hard. For hypergraphs, it gets a bit technical. You need to distinguish more cases and an extra condition. Okay, well, this is an example for graphs still, like we have the 2 switching sets, C1, C2. The constraints are satisfied, the constraints of the switching. The most important one for the switching to happen is the red one, as I already mentioned. So if we look at every vertex, well, V1, for example, in D has exactly C1 as a neighborhood, right? Nothing in C2, so we are fine. Some switching will happen. And actually the switching that will happen is that from C1, the adjacencies go to C2, okay? The other conditions are also satisfied, okay? This was, yeah. And I mentioned that for the example, I wanted to focus on only 2 switching sets, but this is a more general procedure that requires 2M switching sets because you always switch in pairs. So you need this pair condition also. And this more general switching has been published after the 2019 paper. Okay, now we go to hypergraphs, and the statement looks pretty similar. Only one new condition appears, and of course some technicality things also appear. So now we start with a uniform hypergraph, and we're going to extend the Wang WQH switching that we just saw. Again, you want to split the vertex set of your hypergraph into subsets, right? Some of them correspond to switching sets, and the rest to D, the things outside the switching sets. The condition, again, we are doing it the simplest case, only 2 switching sets, but this can be extended accordingly. The condition of the order of the switching sets is still required for the hypergraph setting, no surprises here. You need this extra condition that we didn't have before, otherwise there is no switching happening. So you need that any edge has at least k-1 vertices outside the switching sets in the D set, okay? And then the third condition is analogous, so we just need to write it in terms of the neighborhood of a set of vertices in the hypergraph. But if you remember, like the condition was like, if you look at the neighborhood of in that case was a vertex, but now like we have a set intersecting the switching sets, you had exactly C1 or C2, yeah? And the second condition was analogous also. So to construct the hypergraph, now what we do is like, whenever we had this red condition, we switch the adjacencies, okay? Similar as before. And we guarantee using this procedure you can construct eco-spectral hypergraphs, not cospectral hypergraphs. So that's also a bit annoying, but okay. And then this condition 2, if you look a bit closely, like it tells you that the second extra condition we didn't have in the case of graphs, it tells you that C1 union C2 actually just needs to be a co-clique, an independent set in the graph, in the hypergraph. Condition 3 considers the neighborhood of k-1 vertices. So that's also a small difference regarding the graph case. But let's look to an example. Now we have a hypergraph here. We have 2 switching sets, C1, C2. Each contains 3 vertices of the hypergraph. So the first condition is guaranteed. Second condition, as I mentioned, is a technical condition you need in the proof. Every edge has 2 vertices in D. So this is D. So there are 2 vertices. This is the important condition. So if you look at this subset V1, V2, the neighborhood of this is exactly C1. No neighbors in C2. Yeah. So you need this type of condition to have some action in the switching. And then you have the counting condition that also needs to be satisfied, but doesn't imply anything for the switching later on. And which edges do we switch? Maybe someone can answer to that. I have colored the edges in 3 different colors. Which ones are we going to be switching? See if you're paying attention. There are not many options. Only red, only the red ones. The 3 hyper edges are going to be switching to the neighborhood of C2. Yeah? Indeed, point for Crystal. Yeah, and indeed the statement is a bit more general. For the illustration, I put only 2 switching sets, but this holds more generally, same as for graphs. Huh? No surprises there. Okay, now we switch to the case of a different representation that people also have been looking at in the literature, and we are going to see. Someone wants to answer to this? Seems no. Okay, I'm using the computer of Kathy, I think. So now the representation we are going to be using uses matrices, like Laplacian metrics from before, but a different metrics in this case, we will see. This definition, sorry? Yeah.
We don't have to follow generic somehow question, which, for instance, when we talk about like eigenvalues, particularly easy if you consider graphs, consider regular graphs. So every vertex has, the same number of matrices.
Mhm.
And in your case, you consider K uniform, and you can also consider D regular. K uniform, which are D regular. And so can you just give us a general answer? Does switching not apply at all if they are regular?
Oof, we didn't try that.
But it seems that it is when you think
Yeah,
about
yeah.
like, what switching. So somebody has, and kind of even within graphs, you would forget about hypergraphs. If you switch, so your degrees change.
Yeah, we did. I should think a bit about that. Oh my God. We're getting, I should think about that. We didn't think about only assuming regularity, what would imply. Yeah. Yeah. But it's a good question. I mean, something to think about. Okay. So the matrix representation for hypergraphs was introduced, as far as we saw, by Feng and Li in '96. And similarly was also used by Sarkar and Banerjee in 2020. And it was introduced also in the context of switching, in the context of methods to obtain cospectral hypergraphs, okay? But totally different representation. So now your adjacency matrix or matrix representing the hypergraph contains the number of hyper edges, or the number of edges, if you want, that two vertices have in common, yeah? So from, for example, like B3, B2, B3, B1, there's two in red, B3, B2, we only have one, etc., etc. So you see the pattern, okay? So this contains the number of edges per entry between two vertices, I and j, Bi and Bj. There is a drawback of this definition that one can already see quite quick. It's like if you look at multigraphs, you obtain the same metrics. People have been using the same representation for multigraphs. That's not desirable because you're going to be confusing multigraphs with hypergraphs with using this representation. Here we have a very tiny example, this booty graph, that gives you the same metrics representing the hypergraph as the same metrics representing the multigraph. So that's not desirable. So there are some drawbacks with this definition. On the positive side, eigenvalues obviously can be computed in polynomial time. Here, it's as a matrix. So I wanted to give a bit of an overview of the two methods, because for us it was also useful to realize, okay, what is actually what people should be doing or using? We were not sure ourselves when we started this project. So as we saw, for the tensor, you can fully reconstruct the hypergraph by using the adjacency tensor. So that's very desirable. That's not the case for hypergraphs. For the matrix representation, we saw that with the lace example. For tensor, the edge list is trivially obtained. For a matrix representation, the edge list needs a bit more work. For tensor, there exist spectral characterizations. Not much is known for metrics for an obvious reason, because it seems the matrix doesn't say much about the hypergraph. So you see, like, yeah, computationally, one is more powerful than the other one, but representation-wise, one is stronger. So again, I don't have a good answer of what we should be using for a spectral hypergraph theory. This could be also a topic of discussion in this workshop, maybe. And also the second representation, the one using the matrix, has been apparently more used in applications, which is also probably interesting for this audience. Similar as we saw before, like I'm not going to go too much into the details, like one can reproduce the WQH switching for graphs to the matrix representation of hypergraphs. Obviously, the conditions are going to look very different because now we are dealing with counting things in matrices and not with tensors. But similar conditions like the sizes of the switching sets Cs need to be constant. We had that before. We also have an extra condition. So these are technical conditions. They are not very intuitive. Like they just pop up when you try to prove things for hypergraphs. You get extra things you need to put in the statement. The important condition, as we mentioned before, is always a red condition, meaning like the intersection of the vertices in the outside the switching set needs to give you exactly one of the switching sets in particular. And again, as before, the switching will happen between C1, C2, or depending on which one which pair you are looking at of switching sets. Okay. And the blue condition is the one about requiring equitability, which yeah, it gets a bit technical, but it just requires certain equitability condition in your hypergraph. Similarly as before, another example here, like, well, I think by now you should manage to more or less see when switching is happening. Again, I put in red the hyperedges that are going to be switching. And the rest are the technical conditions that need to be satisfied, okay? So again, we go from C1 to C2, okay? And this gives you a non-isomorphic hypergraph. So things that one could do now is like we could try to understand which hypergraph properties, using this type of new methods, which hypergraph structural properties do not follow from the hypergraph E spectra in this case. So this is something we didn't exploit much yet. We were just busy developing the methods, but it would be also interesting to understand, okay, is there any hope for a spectral hypergraph characterization field? We're not sure. So maybe playing a bit more with these methods, we can understand if there is some hope or not on that. So in order to conclude my talk, this is a little bit the overview of what we did. We overviewed the graph case of methods to construct cospectral graphs, semi-spectrum graphs. We have extended the results that were extended already for tensor and matrix representations of hypergraphs to the newest switching, which appeared a few years ago in the two theorems. But there are other methods that have not been explored in the context of hypergraphs. So there is still potential for new results in this line of research. I remember when I was visiting Leipzig with Rafaela, we talked a little bit about that in the context of oriented hypergraphs. I forgot what we did exactly. Maybe we can try to think back about that. But there is definitely like room for new results in this direction. So yeah, as I mentioned here, it would be interesting to know which other results from a spectral graph theory admit extensions to hypergraph theory. Many of them already have happened, but not so many if you put the spectral warp in front. Which other tools could we use to derive new spectral hypergraph characterizations? We don't have many tools. In graphs, we have more tools. We can count walks, we can do things using eigenvalues. Here, we don't know much. So again, we don't even know exactly which is the right eigenvalue representation, which makes it a bit challenging, the whole field. It would also be interesting to see if, so when people justify why cospectral graphs, now going to the basics again, are interesting, many of the times you find reasons that go back to chemistry also, because apparently certain hydrocarbon molecules, whenever they share the same spectrum, they also share some chemical properties. I have no idea if a similar story holds for hypergraphs, cospectral hypergraphs. That's also something totally open. So trying to understand, trying to interpret cospectral hypergraphs is also quite wild and open, I would say. And maybe we can discuss this week. So this was my talk, and yeah, thank you. If you want more details, this is the paper. Thank you for your attention.
Thank you, Aida, for this very nice talk. As you have accidentally seen from the screen, we have some yummy food. So maybe we have time for one question before moving to lunch.
Okay. So I'm aware there's work in studying tensors and identifiability. So this is a question, right? Given your tensor, you basically study some of the algebraic geometry, you're looking at points in a secant writing and asking something about the pre-image, the dimension, if this is identifiable. So it's not exactly your reconstruction problem, but it made me think that you're also saying, giving some spectra, right? And some vertices, can you recover?
Equivalence, yeah.
So it felt like very
analogous, yeah.
It felt like it had similarity, but I didn't know if you studied.
No, we haven't looked at that in the context of.
Flavors, I think.
Yeah.
It doesn't work exactly.
I mean, again, could be one of these connections that is there. I'm not aware of, but it would be interesting to check. Yeah. Thank you.